Everyone
Yeah. This is
doing okay?
yeah.
Yeah.
Making it through.
So I'm gonna do a very quick review on quiz 5 we did last week, really quickly, and then we are going to move on to a very important topic called 2's complement adder and subtractor, which is a lab next week. And it used to be a 2-week lab, but I think you guys are just super smart. I think we can do it in 1 week. I will cover more details, give you a lot of more information, give examples instead of what I did last semester or 2 years ago. I just directly tell them what I want at the end, but not giving them a lot of information. So this time I'm gonna go through the details and tell you the circuits, give you some modules coded up in the class just in front of you. So I think it's very doable to get it done in a week. So this afternoon will be the traffic light control lab. I went through the algebra and truth table last week, so I think you guys can follow the there's a lecture video, I think, over here, and notes and videos to find out the truth table and how did I derive the logic over there, right? And but today, after reviewing quiz 5, we are going to talk about the lab next week because there are a lot of things to cover. And there will be a quiz on 2's complement, so please pay attention to the calculations today, because there will be a quiz on Tuesday next week on 2's complement. I don't want to directly just because this is not as straightforward as all these VLSI transistor drawing. Probably need a little bit of time for you guys to practice. So that is why the quiz will be next Tuesday, not inside of today or this week. And on Thursday, it's going to be a new tutorial. Okay, even though it's pretty long, not really long, average length, but it's mentally easy because these are just memory components, IPs. It's very important to know how to use the IP from Vivado because all these IPs are free. But in the future, when you are designing a ASIC, it could be a commercial IP. You have to purchase it, like all the ARM IPs, all the ARM CPUs, right? All these companies like Qualcomm have to purchase the ARM CPUs and place them in their IPGA design to verify it. If it's getting verified, they will move forward with the ASIC tape out or fabrication of the real chip. Okay, that's usually how things work. But it's good to know how to use, or it's very important to know how to use the IPs. So on Thursday, it's going to be a memory IP provided by Vivado you can directly use. And this will be used as a memory, instruction memory for our soft core lab. So this is what you can expect, okay? So there will be a Pico Blaze soft core. So the Pico Blaze is a Xilinx open source CPU, okay? It's definitely not as complicated as ARM, all these ARM cores. But it's a core. So eventually we will use this core and put our assembly instructions into the memory components, like what we are going to use today, and eventually let the CPU take out the instructions and do all this computation in it. So it's going to eventually will be a very simple microcontroller being implemented on FPGA. It's really exciting, actually. I'm thinking about, because in the past 2 years, what we did over there was we get a microcontroller implemented on FPGA. Then we just program it like blinking LED or control a certain sequence. It's really simple. So hopefully this year we can explore some of the interrupt the functionalities of the microcontroller a little bit. Be more fun. Okay. So now let's come back to the quiz question. I believe I have a solution somewhere. Okay, it should be here. Lab 5, quiz 5. Okay, so the question for this one is we're going to use a switch to turn on all of the counter that counts by 1 on the LED lights, right? So you can imagine it's going to start counting towards 16, and then if you turn on switch 0, it will reset the counter. Okay. I think maybe 1 or 2 of you guys got 100 or 90 something. Another 50% are receiving maybe 50% of the credits, and so it's still at the very beginning. So let's take a look how we usually program it. So from the top, let's take a look. Can you see it? It's just so small. But I posted to Canvas. If you couldn't see it, you can open it up from Canvas. There's a solution over there. So it's on the quiz 5, and I usually after we did the quiz, I will add the name of the quiz as quiz 5 and solution. So the solution will be posted over there. So let's think about it. So it's basically a top. So the top should be really simple, right? If you think about the top, it's basically just a switch, one switch. Okay, and a bunch of LEDs. All right. So in that case, you just name a module. Okay, input clock, and input switch, and output LEDs. These are IPGA hardware resources. So there's nothing like rag or wire. You don't need all these kind of things. These are directly connections. Sometimes it's getting confusing. When do we use wire? When do we use rag? But for the test bench on the IPGA, for all these kind of direct connections, you don't need to give a certain type of it. So eventually just input, output, and software keywords. Okay, clock, switch, and LEDs. A lot of times you program in the exact way we have been doing. Eventually, you are still seeing errors. So if you have a lot of experience, usually you should know that, if you couldn't find out any big issues, the problems could be really tiny or minor problems somewhere else, hiding somewhere. When I was doing the programming, most recently, I'm 100% sure the code is right. I was looking at everything. It's 100% right, and it's still not going through. And I eventually find out I declared the switch as the output. All the little tiny things, it's hiding somewhere. Just be patient and trust yourself whenever you are debugging your code. You know it's right. It must be something minor hiding somewhere, okay? So it's just a one-liner for the code. Super simple. Make the connections, okay? Instantiate the counter, which is some module. We'll talk about that a little bit very quick. And it's a device under testing, and just make the connections. So always get the easiest one done first when you are seeing a quiz like this in the future, right? And it's being implemented on the IPGA. You know the test bench is super simple. Okay, that's it. So get this done first. What are the ports I need, right? Think about the sub module. Oh, the sub module need a clock. The sub module need a switch input. The sub module need an LED output. Okay, now let's do the test bench first. So start a program to the test bench. 1 minute, get it done. So you got a lot of stress of your shoulder. Okay, then move forward with the sub module. Okay, you can imagine whenever it's counting, you need some sort of timer or counter, okay? Because your eye can resolve it, which means you need a counter max and counter, because the digital system usually run really quickly. So if your eye can resolve something, you must need a counter. Okay, it has to count to some certain count max. So that is why we need a count max. Why not just type it in? Okay, open up a sub module, just type the things you know first, and then start gradually adding the things you think are necessary. Okay, could you type this one there first? Okay, if it's counting by 1 second, you know that you have to have a parameter count max, which is 32-bit. The length doesn't really matter. For now, it can be longer, but if it's 1 second, can we just use like 32-bit decimal number 100 million here, because it's running at 100 megahertz? So let's just do it. Just type the parameter here first, and then you need a counter to reach this count max. Okay, because this guy is 32 bits, so your counter has to be 32 bits as well. Okay, give a counter, and the counter is counting internally. Keep in mind, it's a register type, 32 bits. Eventually, it's just a counter with 32 D flip-flops. We'll cover more about D flip-flops later, but If it's able to count to itself and latch it, it has to be a register. If you do a wire, it's going to report errors. So it has to be a register to form a counter. Okay, so the counter has to be a register type, 32 bits. And it's a counter. Okay, and then keep typing, and I want everything to be clocked. So it's following a certain sequence. It's going to update everything at the same time, so I can synchronize all the signal lines. Behavioral is called behavioral modeling, which is one of the most popular ways to model it. Okay, so behavioral modeling always at a positive edge of the clock. You can use a negative edge of the clock, doesn't matter, but usually we just do a positive edge of the clock. And then because the switch, if we turn it on, we want to start counting. If we turn it off, we just reset it. Since we are assigning values to this LED variable, okay, we are assigning values to it. Use this, it's called procedural assignment. Usually we use this blocking assignment. So in that case, it has to be a register type. So you can find out a lot of times we hope the output can hold the value for a certain period of time, can latch it. So we usually give that variable a reg tab, since we know that eventually this signal will be shorted to this signal line, which we don't declare anything, but usually just a direct connection, could be a wire type of the IPGA. So we buffer it in front of it. We buffer that signal right before that IPGA output, so it's able to latch it. But after you are able to latch that signal output and buffer it over there, all the following lines doesn't have to be buffered because it's already latched or being controlled by the clock. Okay? So you can make a direct connection to the IPGA signal lines. You don't need the two register types. Why do I have to do that? Like two latches, you control it twice. It's not necessary. You just need one stage of latches, right? So everything's being controlled. Whenever the signal is over here, just clock it. Everything will be kicked out from that register array, okay? And eventually it will be sent to the IPGA's signal lines. It's just a convention of the modeling. That's why we do it, okay? So in your sub module, keep in mind your sub module right before, if I draw it here really quick, probably it's more helpful. Okay, here's the top, right? You got LEDs. That's a keyword. And right before it, okay, you buffer it. So that when there's a clock arrives, all the data will be kicked out from the D flip-flops. Okay? So in that case, in your sub module here, your output is getting buffered. So you'll need that LED to be a register type. Right, register type. But eventually, if you switch it off, because that's an else covered by the else case, right? So if it's switched off, you give a 0 to LED, which means you are resetting all the LEDs. It's a lot easier than you thought, right? Okay. So when switch is off, give 0 to the LEDs. Okay. So now let's start typing the most complicated part of the lab, of the quiz. So when switch is 1, see how I do it? I do the easier ones first, and eventually move to the most complicated case. Okay? So this should be the last case you want to deal with. And you are receiving a lot of partial credits by doing all the easier ones first. Okay? And then you move to this one, right? So when switch is 1, it's operating normally. Okay? So if it reaches count max, I want to reset the counter and add a 1 to LED. I can do this comfortably because I know it's a register type. They're just D flip-flop arrays. I can deal with it. I can just adding things to it. I can move things. I can shift all the bits. I can assign values to it, or I can adding 1s, adding 2s to itself, because they are register type variables. Okay. If it's not reaching count max yet, just adding 1 to the counter. And that's everything, done. Okay? It's good to look at this example so you know what went wrong when you are doing the quiz. Should we do this again at a later time? Similar ones?
Yeah.
Okay, because the solution is posted. So whenever you have some spare time, just staring at it, right? Trying to go through this for 100 times. Make sure next time you know where to go. Okay, so start from here, get it done. And then starting from here, and you know that LED need to be buffered. And you know that you need a parameter. And you know that you need a register type. It's not a port because it's counting internally. So it's counting internally, I don't need to export it. It's not having any interaction with the outside world, right? Just counting internally. Any question on this? It's good to have a summary, right? You know what you are going to do next time if you see a similar problem. Okay, now let's look at 2's complement. How many of you still remember what 2's complement is from logic? 2? No? It's challenging. Okay. So Tuesday there will be a quiz on 2's complement. So this week, let's just focus on this because the lab is a bit challenging. It used to be 2 weeks, and I'm putting it as 1 week lab together. So eventually, it's just more tasks and it's a bit more challenging. So we'll start going through this from today. 2's complement is a way to represent negative numbers in the computer systems. It's in the modern computer systems, they all use 2's complement. So for example, for this is plus 3, it's positive 3, right? If you want to convert positive 3 to negative 3, for the 2's complement conversion here, you need to flip all the bits first, and then add a 1 to it, and that becomes negative 3. 1, 1, 1. Wait. 1, 0, 1. Right? And this in the computer system, it's going to be recognized as a negative 3. But physically, is this really negative 3? No. What is this? 5. But in the computer system, I just tell the computer, just fake it, okay? This is negative 3. Just treat it as negative 3. This is what's really happening. Okay, so because it's not really negative 3, so when we are doing all these adding, subtraction, multiplication, all these kind of things, it's creating errors. Okay, when it's creating errors, we need another set of rule to tell the computer, hey, if you see this kind of error, this is what. If you see this kind of error, this is what, right? Yeah. So like telling one lie, how to use another lie to cover the first lie. Similar, right? Yeah. So that's where this comes from. Keep in mind. All right? So, but we don't want to just always converting things back and forth. But you can tell that whenever the MSB is non-zero, you know that it's exactly a negative number, right? For sure. Before you know what that number is, but you know if the MSB is non-zero, it's a negative number. It must be a negative number. So in that case, I can convert it back to its positive version. For example, 1, 1, 0. Okay? MSB is 1, so I know this is negative. So what is the positive counterpart of it? How to convert it back? Because you can see you flip it and plus 1, right? So if you convert it back, you minus 1 and flip it. So you minus 1, what is this? 1, 0, 1, right? And flip it. 0, 1, 0. So what is this? 2. So what is this number? Negative 2, right? It's not really convenient. It takes time. So what's the best way to do all these 2's complement conversions? So the rules here, the rules here are For the IMSB, we treat it as the negative counterpart of that, the number at that digit. So for example, this one is what? It's at 4, right? So this digit is actually 4. So we, in 2's complement, we always treat this guy as -4, but not 4. And all the rest are positive numbers. We adding to this number, so this is 2, this is 0, so eventually we're getting -2. Did you learn this in logic?
Yeah.
Okay, it's how you convert it, right? So if you see a pretty big, a lot of digits,
Large negative.
what is this?
Sorry to count.
Yeah,
It's
yeah, but after this class, during the interviews, you need to let whoever interview you know this number immediately, okay, in 1 second. All right. It's gonna be -1. Why?
Oh,
Because this is the negative, the largest, right? Whatever negative, 1, 2, 3, 4, 5, 6, 7, 8.
yeah.
Okay, and all the rest are positive, and added together, it's just a one number less than whatever this absolute value is. Eventually, no matter how many ones you have, what is this?
That's -1.
What is this?
It's also -1.
Like a million of ones. Still -1
Yeah.
in 2's complement. What about this?
It's -2. It's also -2.
Because it's going to be -1 minus 1, right? So this positive 1 is gone, so it's -1 minus -1. So eventually it's going to be -2, no matter how many ones you have. So in that case, for 2's complement, if this, you know this is -2, right? So adding ones in front of it's not changing the value to it. Agree with that?
Yeah.
Okay, also for 2's complement, what is this number?
This is 1.
It's +1, right? It's +1. And you're adding zeros in front of it. It's not changing the value of it as well. It's always +1. Okay? So now we know how to calculate the numbers. So like if I'm giving you this number here, how do you find out what that is? This number is what? Negative what?
It's -8.
8.
Yeah.
What is this number? Plus
2.
2. What is this number?
-6.
Okay, so these are the ways to recognize the 2's complement numbers, negative numbers. And now let's do the binary calculations. There's a definition called overflow. This overflow is a little bit different from the overflow of the C++ programming. Sometimes you get carry out, you call it overflow, right? But in here it's different, keep in mind. If I'm asking if there's an overflow happening for 2's complement calculations, you need to be able to figure that out. Okay, it's not carry out, keep in mind. Sometimes there's carry out, but it's not overflow in 2's complement. So overflow only happens when you have p plus p and you're getting an n, or n plus n, you're getting a p. Keep in mind that's only 2 cases for the overflow in 2's complement. Only 2 conditions. If you have a p plus n, you're getting a p, but there's carry out. It's not overflow. P plus P, you're getting a P, no overflow. N plus N, you're getting an N, it's not overflow, even though there's carry out. No overflow for these cases. So the definition for this is very useful. So after the lab next Tuesday, you will be able to find out why it's useful, because we need that logic to generate that overflow bit for the calculations. So only these 2 cases are called or defined as overflow, because if a positive number plus a positive number, how are you getting a negative number as a result? It's impossible. Okay, so that's why we are, have to use a second lie to cover the first lie, right? So if you have a negative number plus a negative, how can you get a positive number? It's impossible. All right, I owe you $10, eventually you owe me $20. That's so sweet. Right? So let's look at some examples over here. 111 plus 100. That's basically negative and negative numbers, right? And 1, and carry out 0. So don't look at the fourth bit for now. Just look at this MSB. And we are treating this guy as a positive number because of 0 over here. And then we want to decide what kind of MSB we want to use. It depends. Okay, it's not always happening like whatever carry out you have, you just directly use it. It's not always giving you the correct answer. It's not always giving you a correct answer. Maybe this example is giving you a correct answer, but not always, because it's 2's complement. It's a lot of numbers are being faked. These are not negative numbers, right? So eventually you are getting a wrong number here. But by following the rules defined by the calculations, standard rules, we'll always be able to find out the correct answers. Now let's look at this one. So n plus n is p, right? In the n plus n is p. So whenever overflow happens, so overflow occurs, we want to adopt C2. That C2 is the final carry out. The final carry out, which we should adopt it. So it's going to give us the correct answer. Because this, before you use a carry out, you are getting a positive number. That's why it's n plus n getting a p. And now it's at the moment that you want to decide the C2. Should we use a carry out? Should we give a 0 to it? But eventually, if you give a 0, it won't be correct because it's negative plus negative. It shouldn't be a positive. If you give a 0, it's going to be positive 3, right? So it's going to be wrong. So in that case, we have to use this carry out here, and which is giving us, this is negative 8, right? And this is plus 3. And eventually, this is negative 5. And that makes sense because all the 1s is negative 1, which is learned it, and this is negative 4. So negative 1 plus negative 4 is giving us negative 5. And eventually, if we adopt carry out, it's giving us a correct answer. Let's look at another example. 111 plus 101. It's n and n, so it's negative 0, 0, 1, carry out. So it's n plus n and giving us the n here, right, for the MSB. Now is the moment to decide if we want to just use it, or it's always the same answer, but it matters when you are dealing with the hardware, right? But now let's look at it. N, so there's no overflow, right? If there's an overflow, we want to duplicate S2. So this is S0, this is S0, S1, S2, duplicate S2 to C2, or use S2 as C2, even though it's still the same number, right? Remember, when you are adding a 1 in front of it, it's not changing the value of the number, right? So this is negative 1, this is what? Negative 3, and what is this? Negative 4. Still correct. Okay. What about this? 0, 1, 1, 0, 1, 1. P 3 plus 3 should be 6, right? It should be positive 6. 0, 1, 1. PPN. Overflow happens. overflow occurs. So what should we do?
Add
Duplicate C2, right? What is C2 here? There's no carry out. So C2 is 0. Duplicate it.
so
Do I have a better example? Let me see another example. For example, 1, 1, 1, 0, 1, 1. Let's see what's gonna happen here. So this is NP. So we know there's no overflow. When there's no overflow, we should use S2 as C2. Okay, now let's see. 0, 1, 0, and there's a carry out actually. Okay. If you don't follow this standard or the procedure here, we are going to use it, right? If you don't use the 2's complement, you are just doing addition by using hardware. Hardware doesn't know what to do. If you just use the adder, and eventually it's going to use this C2. So you are getting what? You are getting 1, right?
yes.
Yeah. If we don't follow this kind of rule we just set up over here, just very simple addition by the adder. You're adding a binary number to a binary number by the adder. So the adder's hardware is not changing. Okay? So it's add it together, and eventually you're getting 0, 1, 0, 1. Just by adding it to it. So what is this number here right now? By following 2's complement rules.
It's -8 plus 2, so it's -6.
Right? What is this number?
It's -1 times 3.
Yeah?
So it should be -2.
Plus 2, right? So this is
Oh yeah.
2.
Sorry, plus 2.
See? Got issues. Because you lied at the very beginning. Why you lied at the very beginning? Because this is not -1. What is this number? Just looking at the binary numbers, unsigned. What is this number? 7. What is this number? 3. What is this number? 10. It's correct. By adding the binary numbers together, it's correct. But you lied about it. You told the computer, this is not 7, this is -1. And this is 3. And this is -6. Eventually you are having issues. That's why you have to follow the certain rules that we just set up. Now let's come back, see if this is going to make it happen. Okay? Overflow or not?
Yes.
By looking at this guy. NP, P. Right? NPP. Overflow or not?
It's,
No.
no.
Why? Doesn't satisfy any of them. Overflow or not? No. So in your Verilog, always think about it. Why we set up these rules? Because it's super easy to implement in Verilog. It's just simple if statement. So if overflow, then do what? Do a concatenation, right? You put the C2 over there in front of it. I must be with a curly bracket. Okay? If no overflow, we put S2 in front of it. Just S2 and S2 to as whatever the rest. Okay? It's all because of the hardware. All because of the hardware. NPP, no overflow. What are the rules whenever there's no overflow occurs? Duplicate S2 as C2. Duplicate this guy to here, which is 0, right? Then becomes positive 2. And now it's correct. Make sense? So keep in mind, always look at PPN and NP. Satisfies, then adopt C2. Whatever C2 happens for the adder, just use it. No overflow, duplicates S2 as C2. The reason we want to do that is eventually the final result could be a concatenation. That's the final result. When overflow happens, when there's no overflow. All right? So now let's look at the adder's computer architecture, the architecture of the adder, subtractor. We don't have time to derive everything. It probably will be derived in the LSI class. But now, just give you guys a conclusion. So for a 1-bit adder, okay, FA, full adder, it's a full adder. Carry out is what? A or B,
or C.
CI or AB. Because a full adder has a carry in and carry out, and it's adding A to B. How many inputs are there? 3. So it's a 1-bit full adder or 3-bit full adder?
Yeah, this is a 3 bit.
1-bit full adder. Why?
Oh, because the carry.
There's only 1 bit. It's adding 1 bit to 1 bit. So what is S? A X or B, X or CI? Okay? So whenever we have FA, CI, I usually call it C0, C1, C2, A0, A1, A2, B0, B1, B2. These are the sums. S0, S1, S2, C2. So for unsigned binary numbers, these 4 bits will be the final result. Now, because the computer has sign, or the numbers has a sign, so we have to deal with the 2's complement numbers. In that case, we have to design a logic to figure that out, right? So first, how do we do a subtraction? How do we do a subtraction first? So A minus B equals A plus minus B, right? So in that case, we need to convert B to its negative counterpart. So in that case, we have to use the 2's complement rules for subtraction. Okay. Even though I put a B here, but now I'm trying to deal with A. It's the same. Okay. So for example, B2, B1, B0, add A2, A1, A0. Or add a negative A2, A1, A0. So this structure should be able to do both subtraction and addition. So the way we do that is we add a little XOR gate here. Instead of directly feeding A's to the FAs, we add one more structure, one more layer above it. Okay, A XOR 0 is what? So if A is 0, 0 XOR 0 is what? 0. If A is 1, it's 1. So A XOR 0 is what? A. So A XOR 1 is what? A naught. Okay? So because 2's complement is A naught first and then plus 1. Flipping every bit and then plus 1. So if you want to convert it to its native counterpart, what you want to do? So XOR with 1, we'll flip it, so we'll finish the first step, and then you need to add a 1 to it. So whenever it's shorted to 1, so make a little switch here. Whenever we switch this to 1, and you want to connect 1 to carry in as well. So whenever 1 is doing the XOR operation with all the A's, it's flipping all the A's. At the same time, this 1 will be fed into carry in, so you're adding a 1 to it as well. So it's like flipping and add a 1. So you can convert that A, 3-bit A, into its 2's complement native counterpart. Any question on this? No question? Did you see the structure in logic? I think Dr. Wells covered it. Yeah. Yeah, he did. Since I saw he drew this on the board when I was walking through the hallway 2 years ago. I saw this FA, 3-bit FA structure on the board. Any question on this? No? So if you switch it to 0, what's going to happen? If you switch this guy to 0, so feeding the one of the inputs of the XOR gates as 0, feeding 0 to it, so eventually A XOR 0 is still A, so it's not changing it. If you are putting a 0 here, A will be passed through the XOR gates, and you are still getting B's adding to A's, because these flatters are doing the adding operation but not subtraction. They don't know which kind of operation need to be done. So all these FAs are only doing additions, okay, because that's the internal structure determine that. So are only doing additions. So you have to convert them into the native counterpart in order to do a subtraction operation. Make sense?
Would you have to do the same for the B bits as well?
B is not changing. So these are to B. So it's assuming that B's are already set there. It's not changing. So it's either B plus A or B minus A. Either way. You can definitely change B's as well if you want. Right? If there's a need to flip all the B's to its native counterpart, you can do that. All right. So now let's derive the logic here. How do we deal with the final results? So when there's overflow, there's an overflow. What kind of bits need to be manipulated? So let's start with A. Okay, let's look at the structure really quick. So what are the bits really matter to determine the C2, like the carry out here? What are the bits that matter? What are the numbers that matter? Can be physical bits, can be some intermediate values generated by the previous bits. A2 and B2, and also the little carry here, right? Yeah. Which is C1. Because if you want to determine if there's overflow or not, you have to look at MSBs. You are trying to determine is it PPN or NNP. So you are looking at B2 and A2s. Okay? And in order to know if there's overflow, you have to know what the final result here is. So eventually the bits that determines if you are adopting C2 or not are actually A2, B2, and C1. Agree with that?
Yeah.
You don't have to worry about this one because C1 is right at the final result of this addition here. Okay, and you have to look at this number because you want to determine its final result is PPN or NP. Okay, and you have to know A2 and B2, so they have to be both zeros or ones in order to make overflow happen, right? So eventually you are only looking at these 3 bits. So in that case, we can make a truth table here, looking at A2, B2, and C1, right? So this is overflow. OV. Keep in mind, it's not 0 volts. It's OV. OV, okay? Just look at all the combinations. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1. Okay? Overflow or not? So you want to let's just calculate S2 first. Let's calculate S2 first, so we know if the final result is positive or negative, right? For the MSB, for this bit here, S2, right? S2. Let's do that first. What is S2? 0, S2, 1, S2. Adding all of them together, S2. 1, 0, 1, 0.
0 and then 1.
Overflow or not?
Not
Overflow or not? Possibly. PPN, right? PPN.
It's like
When they are not the same, there won't be any overflow. No brainer. NNP. Yep. NNN. Nope. All right. Let's see what's the next we want to look at. C2. I probably don't need it for now, but let's just list it. C2. By looking at these 3 bits, you can find out C2. So what is C2 here? 0, 0, 0, 1, because getting carry out here. So we can definitely, because these 2 bits are generated by these 3 bits, right? So method 1 is you can generate this overflow bit by just looking at these 3 bits. It should be fine. You know, it's not a big problem. We can use it because these are inputs. They're available. They're all available. Right? They're all available. Just get a wire here and find the logic and making a combinational logic circuit. Eventually we can find out the overflow indicator. So the overflow indicator. Why? Because we need to put this one in the condition of the if statement. If this is the 1, we do something. If this is 0, we do something else. So we need this indicator. So how do we find the indicator? You can look at these 3 bits, no problem, it's gonna work.
Yeah.
How to find it? OV, overflow indicator, is 1 bit, is
plus C or C, yeah. And then plus A, B, and C naught.
It's gonna work. However, if you look at this truth table, including these 2 bits, even though these 2 bits are generated by these 3 bits, but in order to generate this overflow indicator, how many inputs there will be if I'm trying to generate combinational circuits with all these signal lines? There are 5 inputs, right?
Yeah.
If you have to list all the possibilities, all the inputs, you are getting 32 combinations, 32 entries. Okay, but all the rest are giving you zeros or ones for the overflow indicator bit.
That should
How many combinations, possible combinations could you have for all the 5 bits? Theoretically 32, right?
yeah.
2 to the 5th.
Mhm.
So for all the rest entries, it shouldn't indicate overflow because these are the only conditions that are generating overflow bit. And the problem is all the rest combinations or entries are not even possible. It just won't happen. Why?
Okay, it's just-
Because these are all the possible inputs, and whenever these possible inputs are happening, these are the exactly C2 and S2 they are getting. There won't be any other combinations over here. Okay, so you are not getting a full-fledged truth table to generate this combinational circuit. So in that case, we can, because these are not happening, so we can actually directly look at C2 instead of having all the A and B's involved. If you are looking at just a simplified version, okay? So because all the rest of conditions are not happening, we are looking at C2 and C1. Okay, if you can find a certain logic that covers all the possible inputs and outputs, it just directly use that combinational logic to find out OV. Does that make sense? It doesn't, probably. You know what I mean? So all the rest logic combinations are not happening. These are only possible cases.
Yeah.
Okay? So we are trying to find a shortcut, since we know the rest are not happening.
Yeah.
Now let's come back. Look at it. When this is happening here, when OV is 1, look at C2 and C1. They are toggled. What about this one?
They're not.
Toggled back.
So, because you just exclusively.
Yeah, so they have to be different. So whenever C2 and C1s are different, you are getting an indicate overflow. But for other types of circuits, you cannot draw a conclusion from it because you don't know what other entries are, right? But the thing is, for this circuit, these are all the possible inputs.
Yeah.
Okay? So feel free, just look at these ones.
Yeah.
So eventually OV equals what?
Just C2 C4 C1.
It's a shortcut. It's gonna work. What else do we need to find out the final result for this one? So we know we can add a little circuit here, C2, right? C1 to generate what? OV. Like what we covered at the very beginning of the class. Okay? We need the OV as a condition. If there's an OV, if there's an overflow, what we want to do? Adopt C2. If there's no overflow, what we want to do? Duplicate S2.
Yeah.
Okay. So now what the next step? What should be the next step? Depending on OV, we should generate the C2 final. We call it C2 final, not really C2, because C2 here is not really being used. Sometimes it's not being used. Sometimes I use S2 as C2 if there's no overflow. Right? That's why I have to use the logic, whatever logic in our mind, and convert it into real circuits as a C2 final instead of C2. Okay? the C2 final could be C2 or S2, depending on if it's an overflow or not. So how do we do that? I'll give you 1 minute to think about it. Let's take a break, probably 3 minutes break. Like come back at 9. 3 minutes exactly. Okay. Think about this a little bit.
Have you finished
I haven't done.
We're chilling out of Micron right now.
Yeah, I know.
When we last looked at them, yeah. So maybe that should be like thicker, right?
Yeah.
Okay, so what are the bits are getting involved for that final carry out? So when we're thinking about it, hey, you need the overflow indicator, you need C2, S2, because whenever overflow happens, you adopt C2. Whenever it doesn't happen, you duplicate S2. So eventually, you got a C2 final. It seems like you need these 3 columns as inputs. Okay.
Yeah.
So when there's an overflow, use which one as a C final? No overflow. Which one? S2, right?
Yeah.
When there's overflow, use which one? Adopt C2. No overflow, adopt S2. No overflow, S2. So these two are S2s. Overflow, C2. No overflow, S2.
Yeah.
So C2 final equals what?
Equals C2, no, not C2, S2, not overflow, and then plus not C2, S2, not overflow?
Yeah. C2 not, S2, and overflow not, right?
Yeah.
Or C2 not, S2,
Overflow.
overflow not again. C2, S2 not, overflow, C2, S2, overflow not. And this becomes a quiz. Just joking. Next Tuesday, okay? Study this. This is what? Same stuff. Or logic. Cancel one of them. What can we do here? Which ones can be combined? Common terms here. So C2, so it becomes C2 not or C2, which is 1, right? And S2 overflow not. Gone. It's 1. Right. That's the final logic that you can use for your Verilog. Okay, just assign this logic to the C2 final, and eventually you're putting a C2 final as 2, as 1, as 0 as a final result of the adder. Okay? So how do we design the system? How do we design the system in Verilog? How many modules do we need?
Just a top and a.
So yeah, we need an adder first, right? We can make the adder to be 3-bit adder, no problem. It's just a vector when you declare as a variable. In the adder. So think about the adder. So the adder has switches providing the inputs. Could be switches from, you need a six bits for the A's and B's. So let's say 2 to 0 as A's, right? Switch 5 to 3 as B to form all these 3-bit inputs. And need to carry in. I usually name it as C-1, so it's a CM1. Why it's called C-1? Because it's I like to name this guy as a C0 and C1, so this guy has to be C-1, right? Just a name. So it's a carry in, C-1, carry in. So carry in is the input of the adder. You know that, right? Okay. What else do we need? So this adder already has all these XOR gates inside. Why is that? Because all the logic covers this circuit. Okay. What else do we need? So think about the adder. Let's take one step back. Think about the adder. The whole thing we derived here should be the behavior of the adder, right? Okay. We already know how it behaves, and we already know what the C final is. C2 final is. Okay, the C2 final here. We already know what that is. So we just need to program the behavior of it, right? So depending on the whatever internally programmed, so eventually it's outputting a 4-bit number with a C2 final here. That's the final result. We care less about the internal circuits because we can describe it using Verilog by using this logic, this conclusion here. Okay, shouldn't be difficult. So the only thing is we probably want this adder to update the output at every clock cycle. So we're using a behavioral modeling. It's going to be always at the opposite edge of the clock. So we need a clock. What else do we need? It's probably everything.
I think so.
Yeah.
Just like outputs.
Yeah, the outputs is not ready yet, so the outputs you can use the outputs as display them. You can display them at the LEDs. We can have the LED from 15 to 0, but we are only using probably 4 or 5 bits of it. So we want to display the results at the LEDs at the initial step 1, so to see if we're getting correct binary numbers, binary results. So in that case, you can definitely make a connection, right? Make a connection. This is going to be 4 bits. What else do we need? I probably want to see if overflow happens for debug purposes, right? See if it's operating properly. So we want to overflow as another LED, for example, LED 4. So these are all the inputs and outputs I can think of. There will be some internal connections to a different module, but now for to interact with the IPGA's resources, pin resources or hardware, that's all the things I can imagine. What's that?
I was a little bit confused why we don't draw the XOR gate here, but we have the XOR gates in front of the full adders before.
Yeah, because you can treat the whole thing as a block, right? As a box. So everything here as
That's not a full adder.
the box is being drawn here. So these A's are ports. XOR gates are not ports, are not giving ports, but one of the input is a port for the C-1. Right? We already described the behavior of the whole thing from the truth table. That's why we spend the whole time of the lecture to cover it. So these are all the behavior already covered by the truth table, which have all the XOR's functionality covered by the logic writing.
Cool. I wasn't sure that was the whole block.
Yeah, I think this is easier. This is better. Yeah. If you draw it here, then you have to, deal with this thing probably with another box, and it's going to be another submodule, complicating things. Right. Good question though. So that's a good part of that's the benefit of using Verilog, right? After you can find out the behavior from the truth table, you can directly just describe it. You tell the IPGA to do whatever you want. Just do it. Who cares? Who cares how you did it, right? Just do it. Okay? So it becomes a module, becomes a black box. You only care about the ports. Only care about the ports. Because all the logic covers all the operation. If the ports receive corresponding inputs, it's going to give you a correct outputs. Okay? Because now it's IP. It's the IP you just created. But all these are IPs, right? It's IPs. What's next? Okay, so what are the goals? I want to display the number on a 7-segment display because a lot of people cannot read binary numbers. Okay? So is that easy to do or not? Yeah, so these are the, it's like a digit of the previous lab, right? It's a 4-bit input as a digit of the decoder. So you need a decoder here, right? This decoder could be different because in the previous labs, if it's unsigned, right? If you receive a 1, you have to change the numbers in the lookup table. Okay, so previously your decoder receives this number is unsigned. You are trying to give a pattern of the 7-segment display as 8. It's basically turning on every single LED, all zeros, right? But now it becomes different because whenever you are receiving this, you need to display a what? Oh, it's a bad number, bad example, sorry. Oh, it's too big. Okay, so previously you are displaying a 9, right? But now it has to be a 7. Has to be a 7. So you have to change the numbers, change the patterns in your lookup table of the decoder. So that's for the number digit, and we have to add a sign digit in front of it. So we have to use 2 7-segment display modules, right? 2 units, one as a number, one for the number, one for the sign. So how do you add a sign? How to determine if you want to add a sign to it or not? Just look at C final. If C final is 1, you're adding a bar in front of it. If C final is not 1, you keep it blank. Okay? Is that easy to do? Yes, we have learned how to do that. You're activating each unit really quickly. Right? Activating this one, you throw the number to it, and activating this one, you determine if you're adding a bar or adding nothing to it. So just scanning through the 2 units really quickly. Right? It's either doing a sign management or doing a number management. Okay? So, however, I find out, hey, the decoder needs 4 bits, and LEDs also need the 4 bits. What are the techniques we have learned to deal with it? Always thinking about coding, right? When you're writing code, how do we do that? So eventually you are having two sub-modules having an interconnection. The only way we can do a connection is with the sub-module in the top, right? We do a dot something parentheses to make the connection. But now, in between two sub-modules, we need the interconnections. What are the techniques we used? Wire, yeah. It's gonna be a 4-bit wire. Okay? Generate this 4-bit wire in your top. When you are doing the instantiation, the sub-modules are connecting to the wire, so they are indirectly connected to each other. And what about this one? LEDs are the top. Resources from the top. Can you still connect this one to the wire? Of course. In the top. So you declare this wire in the top. This belongs to the top. And eventually just directly assign these ones to LEDs. Very simple, just equal, right?
Yeah.
What else? Do I need a clock for the decoder? Yes. Always clock it. It's always a good practice. Clock it.
Guess you need some count variables to cycle through the.
Yeah, it's actually, because this one has outputs, right? Outputs to the SAG. Okay, so you want a clock to control it. Clock to control it. So whenever you're having intermediate values, it's waiting, just waiting. Don't rush. So whenever clock arrives, update everything at the same time. Okay, so the decoder takes in that digits input and output it to, and goes through the case statement of the lookup table or the decoder's patterns. Okay, you have to modify it according to the signed values, and then eventually they are shorted to SAG, right? That's a 7-bit bus, and keep in mind you need a decimal point as well, DP. Just turn it off. Otherwise, it's like having a 2.5 volts. It's a very dim LED. Looks bad. You don't have a decimal point. So control the DP as well. So you need to give DP a what? 1 all the time, right? So it's off. Turn it off. What else? Decoder need an AN, right, to cycle it through. So the IPG resource AN has how many bits? 4 bits.
Yeah.
3 to 0, right? What else? That's pretty much everything you can think of.
I think so.
Okay. So by doing this, and you're expecting a result like 2's complement. I just added it, but why it's not here? It's not showing up. Oh, I haven't uploaded to it. Anyway, there should be a demo video that I'm gonna upload to this one. It's the lab. All right, I'm gonna update it. So I recorded the video in the weekend, so it should be there. I'll let you guys know. And that's not everything yet. That's why it was a 2-week lab. So the next step is actually easier because we're adding another 2 modules to this existing hardware. So the goal is to add a serial in, parallel out shifted register. If you have spare time, okay. This week you can start working on this earlier, but eventually it has to be done. Oh, these are carries. Why do I have to do that? So these are S, right? C2, S2. S1, S0, C1, C2, XOR for overflow indicator, and overflow indicator doing some sort of logic with this, right? Something, right, to generate C2 final. Okay? And we got B's. Smell. And switch. C-1. All right. Now the modification are to the A's. A's won't be direct A's from the switch. It will be a shift register. It's really important. Imagine all these serial input communication ports, right? It's all serial, just one line. It's saving a lot of hardware resource from the microcontroller. So people prefer serial compared to parallel from like 80 years ago, 60 to 80 years ago. It's taking a lot of pin resources from the microcontroller. So always serial, even though it's a little bit slower, which is fine. So it's gonna be we need 3 of them. Serial in, and that's the D flip-flop. Shifting. Same clock, synchronized. Clock. Okay? So there's no parallel A anymore, keep in mind. You're not giving like 3 switches. These are the static A's input. Nope. It's a serial in, it's digital serial data. You have to clock it into the register and parallel out. See? Serial in, you give a number, you clock it. Boom. Okay, so this becomes the D for the next stage. You clock it one more time, it's being pumped to another D. And you do it one more time, clock it, it passes to the final D, so which becomes A0. And all the rest are being latched as these points and becomes A1, A2. How do you form a clock? You just use the IPGA's clock. And your hand has to be really quickly, right? Because it counts at like 100 megahertz. So after the 3rd clock, you have to stop it. I'm joking. What's that?
When you say serial and parallel, are you meaning like the blocking, non-blocking?
No. These are. It's a shift register. It's a module. You have to create a module like this. It's gonna be a module. Look at the inputs and outputs. Inputs ISI, input clock, output a vector, 3 bits. How do you clock it? Keep in mind, every time you have to change the value of the switch. So this must be a switch, right? Let's say switch. Just keep it far away from other ones. Switch. Okay, switch 15. I change the value, I clock it. I change the value to 0, clock it. I change the value and clock it.
Yeah. So just add positive or negative edge of the input switch.
Yes, how to do that? Manually, use another switch. And that involves debounce, right? Because every time you switch it on, there will be a lot of oscillations, generating like a 5 to 10 rising edges. It's gonna be a problem. You have to debounce it. So eventually, this clock signal has to be debounced. That's switch 14, for example, and it's getting debounced and getting a clean rising edge for you. Exciting?
I think so. This is basically so you can like input 1 bit at a time into that first module, so then you can save it and then add
Yeah.
the two numbers together.
Yes, it's really satisfying. I modified it during the weekends and it worked perfectly. So you are thinking this is very complicated, but actually it's not. So eventually you can create a little manual clock by your fingers. Eventually you got 3 inputs, right, and then parallel out because they already there. You're not actually have another control layer. Definitely you can add another control layer only when that they are ready. So you don't have any intermediate values. Whenever they're ready, you pump them out at the same time with one more clock. But actually we don't care about that. So whenever you are clocking every single digit in, it's changing the values, changing the output. So whenever you do it for 3 times, after the 3rd time, you know that's the final value. So you have to count for how many times you are doing this. Make sense?
Yeah.
Very doable. I'm going to show you the examples of this one, this module, and debounce is given, okay? And part of this one as well, and the test bench. So it's very doable, okay? We'll see you this afternoon for the lab, for the traffic controller lab.